Okay, here's our video today on Algebra 1. This is the course on Algebra 1. We're going to have a lot of videos on Algebra 1, but we have to start with the prerequisites, right? So this is part 1A, so that means this is the first part of the prerequisites, and then we'll do more prerequisites in the next video, and then move on to the actual course. So if you know these prerequisites, then obviously this is not for you. But so some of these you would have learned in 8th grade. And so here's the first one, need some coffee, right? This is the Pythagorean Theorem. It was formulated by, guess who? Pythagoras, right? So Pythagoras, get my pen out there. We'll use green today. Why not? So Pythagoras, it's really not important for the regents, but if you just want it for your own self, he lived about, so it's a circa, that's the symbol for circa, he about 600 BC, or if you want to see BCE, whatever one you want to use, before the Common Era or before Christ, right? So it's about 600 BCE. No one's 100% sure, but that's where we get this from. So here is the formula, right? This is the equation, right? We know it's an equation because it has a equal sign. So a squared plus b squared equals c squared. So you can see, no pun intended, we have a leg here in the triangle. We have a leg here. And this is called, guess what this is called, right? You should know this. This is the hypotenuse. Fix that y there. All right. And one thing you should know that is the hypotenuse is always, put it over here, it's always the longest side of a right triangle. All right. And we know this is a right triangle. Right? And we should put a box here, right? You should see that box there. So you know that this is a 90-degree angle. And the Pythagorean theorem is used for triangles, right? It's used for right triangles. Okay, so let's get an example. Okay, so let me clear this out. So let's say we had, let me use red now, why not? Let's say that A, the side A right here, this leg right here, let's say that it was 3 units, right? We don't care, centimeters, doesn't matter. And let's say B was 4 units. And so what the Pythagorean theorem will teach us is what is C? How many units is C? And to do that, we just follow this equation right here. So if A is 3, we have to do A squared, right? So we'll just say that right now A is 3, but according to the equation, we have to square it. So we have 3 squared. And B is B. B is 4, so we have to do 4 squared. And that'll equal C squared. So A squared, 3 squared is 9, right? 4 squared is 16. And so that C squared is 25. Now, we're not looking for C squared. We're looking for C. So what is C? Well, C will be the square root of 25. And you should know your square roots. And that will be 5. So that's how we do the Pythagorean theorem. Let's do another example. Okay, so let's say A was, let's say it's 6. And let's say B is 8. So what do you think C would be? Again, we'll just use units. Doesn't really matter what we use. So try to figure that out. Pause the tape if you want. So again, let's just do the theorem, right? We have A is 6, so we have to do 6 squared. B is 8, so we have to do 8 squared, and it will equal C squared. So 6 squared is 36. 8 squared is 64. So C squared will be 100. And we don't want C squared. Remember, we want just C by itself, so we have to take the square root of 100, and we have 10. So if you got 10, great job. All right, let's do a hard one, right? Okay, so here's another example. Be careful with this one. See if you can find what y is. Right? Sometimes they'll have A, B, and C, but they don't have to use A, B, and C. In this case, they're using y. So pause the tape, see what you get with that one. All right, so here you have to be careful. Like, here's the box, right? Here's the box right there. So we know this is the 90 degree. It's just upside down. So actually, this is the hypotenuse. That's the hypotenuse. So be careful. And remember, I said the hypotenuse is the longest side of a right triangle. So this would be leg A, right? That's B, and there's C. Of course, you don't have to use these letters. You can use any letter you want. But let's just use A, B, and C. So we don't know what A squared is, right? We'll just put A squared. B squared is 12. It's 12 squared. And it's going to equal, and we already know what the equal sign is. It's going to be 13 squared. Okay, so we know 12 squared is 144. 13 squared is 169. So we have those answers. So this is just algebra now. We'll just say A squared. So remember, in algebra, we want to get the variable, in this case, A squared alone. So we'll go to minus the 144 on each side. So this is just a simple equation that you should know. And A squared will then equal 25. Now, you don't have to be a calculator here. You can use a calculator, right? But you should try to know at least 12 squared, 13 squared, 14 squared, and 15 squared. Know those. You see those a lot. So if A squared is 25, remember we want the square root of 25. So that means we get 5A, or in this case it's y equals 5. Right? And if you want to double check, we have 5 squared plus 12 squared should equal 169. And we have 25 plus 144 equals 169. So we have a check. Yes. Let's put a sticker if we can find a sticker. Why not? We'll put a sticker, thumbs up. All right, we'll put a thumbs up right there. Why not? Okay. All right, the next prerequisite is GEMDIS. And you may not have heard of GEMDIS. GEMDIS is just PEMDAS, right? I'm sure you heard of PEMDAS. Please excuse my dear Aunt Sally. But GEMDIS is used a lot, especially in other countries. GEMDIS, G is just grouping symbols. Grouping symbols, right? And you should know your grouping symbols. So we have the brackets, right? There's our Alfred Hitchcock bracket. We have the brace, and of course we have the parentheses. So that's why we say grouping symbols. I mean, that's why we say GEMDIS instead of PEMDAS, but it's the same concept. So if you go from left to right, this will be the order that you do things in. So if we did a simple one first, let's say do 3 squared plus 5 minus 10 times, whatever, 6. What do you think that answer would be? Following GEMDIS. Okay? So if you want to pause the tape on this one. So anyway, according to GEMDIS or PEMDAS, whatever one you want to use, right? We have to do exponents first because there's no grouping symbols. So and you should do these one at a time, so you know your mistakes. Sometimes your teacher will see where you made your mistake and give you some credit, right? So 3 squared, we know. Let's change it to blue. Why not? 3 squared is 9. Just follow it through, even if you see the answer already. Right? And then the next one, right? We have to do multiplication. So we have 9 plus 5 minus, keep that minus symbol, minus 60, right? It's negative 10 times 6, right? And then from here, we have to do whatever comes first. Remember, when you're doing PEMDAS, whatever comes first between addition and subtraction you do, and the same with multiplication and division, whatever comes first from left to right. So in this case, addition came first, so we have 14 minus 60, and we get our answer is negative 46. And we create this kind of like a upside down pizza or slice or Dorito, whatever you want to call it. So let's do a couple others. All right, let's change it. Let's use a butterscotch color or whatever this is. What if we had 7 plus 7 divided by 7 plus 7 times 7 minus 7? Now, usually, instead of using this x for multiplication, we should use the dot. You should see the dot more often. And why don't we we'll leave it there for now. So what do you think this is? What would this answer be? And if you want to pause the tape, pause the tape. Pause the tape in 1, in 2, in 3. Did you pause the tape? Maybe not. Well, let's go. So according to GEMDIS or PEMDIS, whatever you're using, we should use division first because division comes before multiplication in the problem. Remember, whatever comes first between multiplication and division. In this case, division came first, so we should do that first. 7 plus 7 divided by 7 is 1. And remember just to follow it out, and then I'm going to put the dot there for multiplication. You follow it out so you don't make mistakes or happy accidents, whatever you want to call it, if you want to quote Bob Ross there. And so your teacher may see where you made your mistake. So now we have plus, we have times, we have minus. So again, we have to do a multiplication now, right? So it's 7 plus 1 plus 49. 7 times 7 is 49 minus 7. How are you doing so far? Right? Now we have plus, plus, and minus. So we're going to do our pluses. We're going to do 8 plus 49 minus 7. Okay. And what's left? We have 8 plus 49 minus 7. So we have 8 plus 49 is 57 minus 7. And our answer is, you guessed it, 50. By the way, there's another concept here. It's called digital root. The digital root is just adding the numbers together. So 5 plus 0 is 5. That's the digital root of 50, right? So I'll keep that up for 2 seconds. 1, 2. And let's do another digital root, by the way. What if I gave you, what is a digital root of, let's say, 99? What do you think the digital root of 99 is? So again, if you add the numbers, right, you're going to have 9 plus 9, which is 18. But remember, 18 is not a digit. We only have 10 digits, right? We have 0 to 9. Those are all the digits in the universe, right? So the digital root will be 9 because 1 plus 8 is 9. All right, let's move on. Okay, we didn't put in the order of we didn't put in the grouping symbol yet. So let's put in a grouping symbol. And what if I did, let's say 6 divided by, put some division there, 6 divided by 2. It looks like we have something printing on the printer. Maybe it's the answer, right? Now, what do you think about this? What would this answer be? You have to be very careful with this one. And by the way, if you lived in World War One, World War One ended. Well, for the United States entered World War One in 1917. But if you went to school and you were doing this problem in 1917, you would get a different answer. But we're going to just do our modern answer. I'll show you both answers. So what do you think this will be? So again, according to, if you want to pause the tape, pause it now. All right. So what do you think? So we have to do, according to GEMDIS or PEMDIS, we have to do the grouping symbols first. Let's use another color there. So we're going to do 6 divided by 2, parentheses 3. All right, seems pretty easy so far. Now, you should know that anytime you see a number next to parentheses, that is multiplication. Right? So this actually would look like this. 6 divided by 2 times 3. Right? So you have to do division first because division comes before multiplication in the problem. So that'll be 6 divided by 2 is 3, and 3 times 3 is 9. So you should have had 9 as your answer. Now, a long time ago, right, they used to have, and some textbooks still have this, so you might get this answer, and this is not the answer. But if you did 6 divided by 2, parentheses 1 plus, oops, where's the 1? There it goes. 1 plus 2, you get the same so far. You have 6 divided by, right, it would be 6, right, because 1 plus 2 is 3, and then they would have multiplied right away, and then they would have got an answer of 1. That is not the answer. But that is what some people a long time ago in World War I and before would have had. So this is not the answer. So let's get a little green marker here. Oh, red. Well, we had red, so we'll just exit out. That is not the answer. The answer is 9. Let's do one more order of operations. Make sure you're clear. Okay, let's do a hard one here, right? And we'll stay with green. Why not? So let's say we had, well, let's put in some brackets. No, braces, right? Here's our braces. And let's say we had -3 times 5. And then we have a brace there. And we had 2 plus 8. And then we had a parentheses. What is going on here? And we had -2 plus, let's say, what number? We'll use 3. And then we cubed it, closed the braces, and then we also closed the bracket, and then we -9. What is this? Oh my goodness. Well, follow the rules carefully and see what you get. So pause the tape. Okay, so this could get messy. So let's put the red there. So remember, let's just concentrate on GEMDIS, right? Or PEMDIS, whatever you want to call it. And we want to do everything within, right? Everything here first. This is what we want to concentrate on. So we don't really care about the 9 yet, the -9. And everything in this red circle or red oval or red whatever you want to call it, we'll use another color. I'll use that. We want to concentrate on the braces first. The brackets, sorry. Remember this, those are brackets. Those are braces, right? Got it wrong. This is a brace. This is a brace. That's a bracket. Unbelievable. Having a little happy accident there. Brace, bracket. Now, let's concentrate everything within the bracket. We want to do the parentheses. So we're really looking at this first. So let's rewrite the whole problem. Clear it out. We have our brace, -3 times 5. I'll try to write smaller here. We have our bracket, 2 plus 8. And we're going to do the parentheses now. So this is going to give us a 1, right? -2 plus 3 is 1, and it's cubed, and we're closing the bracket and the brace, -9. All right, so you should have gotten there. If you want to continue, I'll pause it. All right, let's use another color so we don't get messy here. Again, we want to get rid of these braces, and so we know that's 1, and 1 cubed is 1. So if let's put the brace back in. We have -3 times 5. Let's finish this bracket up. We have 2 plus, and 1 cubed is just 1. So it's just going to be 8 times 1, right? All right, and moving along there. So now we have to get rid of this brace, this bracket. Very confusing, right? Go slow. That's why you go slow. All right, so in here we have 2 plus 8 times 1. So this is just going to be 2 plus 8, which is 10. Don't forget this brace over there. And moving along here now, we have, put the brace back in there, -3 times 5. This is times 10, and that'll end the brace and the bracket. And now just follow along. What is -3 times 5 is -15 times 10. So let's bring this, let's bring this over here. Bring an arrow. Bring an arrow, finishing it off. Change the color. So now we have -150 minus 9. And be careful here. It's keep change. It's -50 plus -9. And guess what your answer would be? -159. All right. So if you can do that problem, you can probably do any order of operation. All right, let's move on now. So now we have real numbers as opposed to fake numbers, right? So we have real numbers, which these are every number you've ever used, right? Going up into ninth grade, all you have used is real numbers. When you get into higher grades, right? And in another video, when we talk about Algebra 2, if you look at the Algebra 2 course, we'll talk about imaginary numbers. Imaginary, right? And they're not imaginary meaning they're fake or they're not real, but they're called imaginary numbers. You might have seen them. They have this I, right? You could have an I, you can have I squared, but that's in, if you want to look at algebra 2. So we're going to just deal with real numbers, right? And let's look at some real numbers. So what is any number you can think of, that's not imaginary, like 7's a real number, right? The square root of 25 is a real number, right? So we're going to look at the list. We'll make a list of going down and what real numbers are. All right, so the symbol, and it really doesn't matter, but they have this symbol for real number, an R. Wow, that's genius, right? So real numbers can be divided. We'll just put the real number here. It can be divided in two parts. The Q means rational, comes from the word quotient. And the symbols aren't important here. And then there's, some people put I for irrational. Irrational. So we have rational and irrational. All right, and so irrational numbers, the most famous one you probably know is pi, right, without the E, the Greek letter pi. And in school we just say 3.14, but on your calculator they'll just go a little farther. There's also phi. You may have heard about phi, the golden ratio. It's another Greek letter. It looks like that, phi. And that's like 1.618. And again, the thing about the irrational numbers is they don't end. They do not end. And I'll clarify that in a minute. So, for example, pi continues without a pattern. And so it just keeps going. The numbers just keep going and there's no pattern to it. Whereas irrational numbers, there will be a pattern that repeats. Again, it's very important that in rational numbers, the patterns repeats. Right? There is a pattern and it repeats. In phi and pi, there is no pattern and it just continues forever. It does not terminate. It does, as far as we know, right? Terminate or end. All right? Let's look at some more examples. So if we look at, and we'll just put, again, this is the real numbers, and we're looking at the rational numbers, right, with a Q, rational numbers. So if I said 3/5, well, if I can make this 3/5 into a decimal, right, and remember when you do that, the top number, the numerator, goes into the box, 5 goes into 3, it does not, so you put a 0, then a decimal, bring a 0 down there, 5 goes into 36 times, and division. So we know we have 0.6. So 0.6 ends, right? It ends. And so if it ends, it's rational. Whereas in pi, which is irrational, 3.14, 15, 92, 65, whatever the case may be, it just keeps going. There is no pattern to this. You don't see a pattern and you don't see numbers that will repeat. So let's do another one. Let's say I had, what's a good one? Let's say we had 7/9. What do you think 7/9 is? Again, you bring the 7 down. The 7 goes in the box. 9 doesn't go into 7. Let's change this color. It's getting a little messy. All right, so 9 goes into 70. How many times does 9 go into 70? What do you think? Well, 8's too much, so let's put 7 there. And that'll be 64. And follow it along. Follow it along. What do you think you get? By the way, that's 63, not 64. What am I doing today? Make that 3 there. It's a bad 3, right? So if we bring that down, you can just notice what's happening here. It just continues to be that. And if it's 0.77777 forever, it's repeating. The pattern's repeating. Right? It just keeps going back to 7. So this will be rational. It's a rational number since it repeats with a pattern. So let me write it here. It has to repeat with a pattern. Or it has to end, terminate, like it did over here. So let's give you another one here. Let's clear this out. If I had like the square root of 25, well, we know that's 5, so that's rational because it terminates, right? square root of, let's say, 169. What do you think that is, right? That's 13. That terminates. But what about the square root of 10? What do you think the square root of 10 is? So this is what you should know if you want to get an estimate, right? So what is it is not a perfect square. And non-perfect squares will always be irrational. So if we look at the square root of 10, right? So we know that if we have the square root of 10 up here, let's use another color here. We'll put some square roots to the left and square root to the right. So what do you think the square root of 9 is? Well, that's 3. And what's the next perfect square? That would be 16. That's 4. So the square root of 10 is closer to 9. So we would say it's about 3 point, maybe we can guess if we had to do this on a test, we'd say, what do you approximately think this is near? Well, since it's close to 10, 9, then you can't say 3.5 because that would round it to 16. And it's much closer to 9. So you might say like 3.1 about, right? That's the about symbol, 3.1. So just remember, anytime you don't have a perfect square, it'll be irrational. So again, just to review that, if it does not stop, it does not terminate, or it doesn't have a pattern that repeats, it won't be rational. So let's clear this out. I'll give you another one. What do you think this would be? 0.010010001 00001, and we'll put this ellipsis here, meaning it's continuing. What do you think this is? Is this rational or irrational? What do you think? As I spin this around. Well, we see a pattern, right? It seems like there's a 0, 1 0, then there's 2 zeros, and there's 3 zeros, and there's 4 zeros. So there's definitely a pattern here. But the problem is we don't see the pattern repeating. So this is irrational. Now, if you saw something like this, 0.010010001, and then it's just a line on top, meaning it's repeating, it's going to repeat back to 0, 1, then that would be rational. Right? So this one's irrational, but if you see that line on top, it's irrational. Like let's say you see 0.765 with a line, well then you know it's going to be 0.765, 765, 765 forever. So that would be rational. Okay, so that's rational versus irrational. Okay, and now let's look at the GCF, right? This is the greatest. I'll put on some pen there. This is something you would have learned in 6th grade, right? This is the greatest common factor, so I won't spend too much time on this. The greatest common factor. So let's just say, what's the greatest common factor between, let's say, 36 and 49? So find that one out. Now, there's many ways to do this. You can do the tree method. Some students like the tree method. You just, make a tree diagram here and just break this down. Like 6 times 6 we know is 36. 7 times 7 is 49. And then circle it when you get a prime number. So you definitely need to know what prime numbers are. And again, you learn that probably in 6th grade. And composite. So prime numbers mean that you can only get that digit plus times 1, right? And that's the only way you can make that digit. For example, we know that 7 is prime. So we'll circle the 7s, right? They're prime, right? Because you can get 7 times 1 is 7. No other numbers will make 7. 7 times 1, that's it, with multiplication. But 6 is composite, because you can break 6 down into, you can do 6 times 1, but then you can do 3 times 2. So if you can do more than 2 factors, it's composite. And you know this, right? So we have 3 times 2 times 3 times 2. Right? And we can't break these down, so this is all the prime numbers there. So now, we call this the prime factorization. Now, do they share any factors? No, if they don't share any factors, then the greatest common factor is 1. They don't share anything. And by the way, if it is only 1, they call it relatively prime. So 36 and 49, the greatest common factor will be 1, or you might hear relatively prime. All right. Well, let's do another one. Let's say, what is the greatest common factor of, let's say, 42 and 36? Again, there's many ways you can do this, right? There is the tree method. If you don't like the tree method, there's other methods, right? We'll do two methods here just to see this really quickly. So we have 7 times 6 is 42, right? And we already know that the 7 is prime, so we'll just circle that for a while. But the 6 is not, so now we have 3 times 2. And we have our 7 times 3 times 2 is our prime factorization there. And in 36, we have 6 times 6, which we have 3 times 2 times 3 times 2. And then we can line them up and see what they share, right? We have a 3 times 3 times 2 times 2 for this one. And then for this one, we'll put the 7 there times 3 times 2. So it looks like they share a 3 and they share a 2. So the GCF, guess what the GCF would be? It'd be 6. Just multiply the 2 together. It would be 6. So if you didn't like that way, there's many other ways. There's the division ladder method. Let's do it. Let's put a circle around here and do the division ladder method with red over here. You just do an upside down division sign, put 42 and 36. Try to space that more so it doesn't look like it's 4,236. And then just think of a number that will go into both of them. Well, we know 6 goes into both of them, but let's say we didn't know that. We just put 2 down. Then 2 will go into 40, and then you just put another ladder box down. You're just making these ladders, upside down division box. So 2 goes into 42 would be 21 times, and 2 goes into 36. What do you think that would be? That'd be 18 times, right? And then we'll keep going. What goes into both of these numbers? Well, we know 3 does. 3 goes into 21 7 times, and 3 goes into 18 9 times. And that's it, right? Because nothing goes into both 7 and 9 besides 1. So we're not going to use that. And so here at the edge here, we have 3 and 2, and 3 times 2 is 6, which we had before using the other method. So whatever method you want to use, that's the GCF. All right, so the LCM, it naturally follows the GCF. And again, this is something you would have learned in 6th grade, but it's important to know for algebra. So let's say you want to know the lowest, remember this is the lowest common multiple. So for example, if we had 3 and we had 5, what's the lowest common multiple? Not factors. You just keep multiplying here, right? Here you can have 6 is there and 10 is there. If you're just timesing it by each number besides 1, and you have a 9 there. 3 times 3 is 9. 5 times 3 is 15. And if you had a 4 here, 3 times 4 is 12. 5 times 4 is 20. And if you had a 5, 3 times 5 is 15. You can stop right there. And this is the box method, right? This is not really a method you should use if you have big numbers, but you can see it right there that the lowest common multiple is 15. So what would you think the lowest common multiple of, let's say, 20 and let's say 32? So again, we can use any method with this, but let's use the division ladder method. Put a little division sign there. What goes into 20 and 32? Well, let's use 2. Why not? So 2 goes into 20 10 times. Put our division ladder there. And then 2 goes into 32 16 times, right? And then we can use a 2 again. And always, slow. Don't go fast on this. Make sure, you're getting the right numbers here. So 2 goes into 10 5 times, and 2 goes into 16 8 times. And if we look at this, and by the way, the lowest common multiple always has to be greater than or the same as the numbers you're using, right? So the greatest common multiple, again, is what number will 20 go into, and 32 in the lowest one. So what do you think is the lowest common multiple of this? Now, with the GCF, we would just multiply the two outside numbers. But with the LCM, once we get where there is no number that goes into 5 or 8 or any of those numbers, you're going to multiply all of them on the bottom like that. So let's use that, right? So just multiply those numbers, the ones on the outside and the last two. And so if you multiply them together, you got 2 times 2 is 4, 4 times 5 is 20, and 20 times 8 is 160. So that'll be the lowest common multiple of 20 and 32. Okay, and the last one for this part of our prerequisites, we'll just do exponents, right? So you should know exponents, like 3 cubed. Remember, that's cubed. This is squared. So 3 cubed is just 3 times 3 times 3. It's right, repeated multiplication. So this would be 27, right? Because it's 3 times 3 is 9 times 3 is 27. And 3 squared, we have 3 times 3, which is 9. So that's pretty easy with exponents. But what if you had a negative exponent? Let's say 3 to the negative squared. What do you think you'll do with that? All right, so when you see a negative number, you're going to take the base and you make a fraction. Just make a fraction, right? So this is 3, the base, so we're going to make it 1/3. And then put the square root as positive in the denominator. So this will be 1/9. And by the way, is 1/9 rational or irrational? So if you did 1/9, right, if you put the 1 in the box, right, so 9 does, we put a 0 there, and what you'll get is you'll just keep getting 1, 1, 1, 1, 1, 1, 1, right, forever. So the pattern is repeating, the 1 is repeating, so this will be rational. So it's 1/9. Let's do another one, right? Give you a couple seconds to look at that. We'll do a couple of these. So let's say I did 4 to the negative third power. So again, the base is 4, so we'll just make a decimal. I mean a fraction. And just make the negative positive. So what do you think this answer would be? So this will be 4. Again, repeated multiplication. 4 times 4 times 4, which is 64. Right? 64, 64, Zoo Lane. I don't know if you remember that one. One more. So again, when you have a negative, you bring it down as positive, and the base becomes a fraction. So one more. What's 5 to the negative third power? What do you think that is? All right. So again, we got to have 1/5 to the third power, or cubed. Again, repeated multiplications. 5 times 5 times 5. So that's 1/125. All right. So those are exponents, right? We can have positive and negative exponents. So in the next video, we'll finish up the prerequisites. It'll be video 1B. So I think we did pretty good today. And what should we do? Let's get an emoji going on there. Let's put whatever this is. Let's do a couple of those. Why not? All right, great job.